At first, Happy Diwali! May this Diwali bring the universal compassion and the inner joy of peace and love and the awareness of oneness to all. So, Happy Diwali again! Welcome back. Today I will say some properties of compact set on topological space and what is the compact set in different topological space. How look like the compact set in different topological space? This is actual goal of this today's lecture. Just recall what is the definition of compact set in topological space. Let X tau be a topological space and here I be an indexing set where small I map to ui. Obviously, the set containing ui where small I belongs to capital I is an indexing family of open subset of the matrix of the topological space X. I map to ui that imply obviously since capital I be an indexing set, therefore capital I map to tau. Since capital I map to indexing set, that imply this ui actually where I belongs to capital I is an open cover of the topological space X. So X equal to I be union of I belongs to I ui. That means for all X in X, there exists I in capital I such that X belongs to ui. And X is compact if ui, the collection ui where I belongs to I is an open cover of the topological space X, and X is compact if this open cover has a finite subcover, that means finite subset, and this finite subset look like F, which obviously contain the index set I. That means X equal to I belongs to F ui. That means if every open cover has a finite subcover, then we can tell this topological space is compact set. Now let's see one example. First example, X be any topological space and X and B convergent sequence. Since X and convergent sequence, that means obviously X n converges to X, obviously this X be the member of topological space. Then the set A equal to set containing Xn union X, where this Xn lies n belongs to natural number union X. Obviously this set A is compact in the subspace topology. I hope my all viewers have understood why I have told in my previous video why in different topology is very important. Why I have told you subspace topology is very important. Have you understood why I have told you? This set A, which contain the sequence Xn and union the limit point X. This set A is compact in the subspace topology. So, I hope my all viewers have understood why I have told you subspace topology is very important. If you know all property of subspace topology, then you will understand this compactness very easily. Okay? Well, let's see why the set A is compact in subspace topology. Suppose that A is open cover of the set capital A, then obviously this script A contain open set in capital A where capital A contain this set, that means by the definition of, since this is in subspace topology, so by the definition of subspace topology, for each U belongs to script A, where script A is an open cover of capital A, by definition, for each U belongs to script A, there exists capital V in tau x such that this U equal to V intersection A. This is the definition of subspace topology. And since A contain X, where X is limit point, so there exists an open set U0 who is containing X such that this U0 equal to V0 intersection A, where some V0 in the member of tau x, and since xn converges to X, therefore in the neighborhood V0 there is many member of xn. By the definition of limit point, there exists capital N belongs to natural number such that xn belongs to V0, and this is true for all n greater than equal to capital N. Since xn is already in A, therefore obviously xn belongs to V0 intersection A, which is equal to U0. This is true for all n greater than equal to capital N. Now choose K belongs to 1 to up to n minus 1. This is an open set UK which contain the script A. Since script A covered the set A such that this UK is such that XK contain this UK. Therefore, the sub-collection which denoted as capital B, script B, since this contain n minus 1 open ball and X contain U0, therefore the script B contain U0, U1 up to Un minus 1, and obviously this is cover X. So that imply, since this is the finite subcover, that imply the set A is compact. I hope my all viewers have understood why the set A is compact in subspace topology. Okay? Well, we all of us know R with usual topology not be compact set, because consider one open cover minus n to n which has no finite subcover which cover R. So R with usual topology not compact, we all of us know. Similarly, R with lower limit topology, upper limit topology, K topology, is not compact. Why? At first consider lower limit topology. How look like the basis of lower limit topology? We all of us know basis for lower limit topology is collection of all those subset which contain closed A, open B, where AB belongs to real number. This is the basis for lower limit topology on R. How we can construct the open cover with respect to the lower limit topology? For this, at first consider the open interval 1, 3. Is 1, 3 is open with respect to lower limit topology? Yes. Why 1, 3 is also open with respect to lower limit topology? Because for all x belongs to 1, 3, there exists C such that x belongs to closed XC which contain obviously 1, 3. So obviously the set 1, 3 is open with respect to lower limit topology also. So since R with usual topology, I have taken the such type of open cover. So we can also take such type of open cover in lower limit topology. Also obviously similar to usual topology, this has no finite subcover in lower limit topology. So by this open cover we can tell lower limit topology on R also not be compact. Similar open set we can consider in upper limit topology, K topology, and similarly it has no finite subcover. So R is not compact on usual topology, lower limit topology, upper limit topology, K topology. In all topology, R is not compact. I hope my all viewers have understood. In topology, different topological space is very important for compactness, because in different topological space, open set are different. Open set is depend on topological space, how the open set would be constructed. This is depends on topological space. So in my previous video I have defined different topological space because set same, but if we take different topological space, then the open set would be different. So compactness would be different. I hope my all viewers have understood this is clearly. Consider x equal to natural number, which is obviously subset of R, and we all of us know in subspace topology natural number is actually discrete space. In my previous video I have seen this, because if we consider this type of open ball 3/4, 5/4 intersection natural number, this is would be singleton set 1. So in subspace topology natural number is actually discrete topology, and this is not compact in subspace topology, because since this is the discrete topology, so here the open cover is look like every single element. That means open cover is singleton set 1 union singleton set 2 union singleton set 3, so on. This is the open cover. Actually the open cover is look like singleton set n, where n belongs to natural number, and it has no finite subcover which cover whole natural number. So n is not compact set in discrete topology. But if X is discrete topology which contain finite set, then we can tell X is compact. That means discrete topology is compact when X contain only finite number of elements. When X contain infinite number of elements, then the discrete topology not be compact. Now I will see new type of topology, cofinite topology. Cofinite topology is those elements tau contain phi and those subset A which is the subset of X such that the complement of A is finite. This is the cofinite topology. Then X tau is called cofinite topology. I hope my all viewers have understood what is the cofinite topology. Cofinite topology contain phi and those A in the set X such that A complement is finite. As for example, consider X equal to 1, 2, 3, 4, so on, and consider one subset X1 equal to 1, 2, 3, X2, consider another subset X2 equal to 3, 4, 5, 6 and X3 equal to 2, 4, 6. Then X1 complement would be 4, 5, 6, which is not finite. So X1 not be member of tau because cofinite topology means the complement is finite. X2 complement means X minus X2. This is contain only 1, 2, which is finite. So obviously X2 be the member of tau. X3 complement is, this is the even number and X is this. Therefore X3 complement would be odd number. This is also contain infinite set. So this is also not belongs to tau. Only X2 be the member of cofinite topology. I hope my all viewers have understood what is the cofinite topology. Now I will see compactness in cofinite topology. Cofinite topology actually always compact topological space because consider X tau be a cofinite topology. That means tau contain only empty set and A, which is subset of X, such that A complement is finite. Consider X be union of open ball, that means X equal to alpha belongs to I, G alpha, where obviously G alpha be the member of tau. Tau be the member of cofinite topology. For this open cover, consider any fixed open ball. Take any G naught from this open cover, this collection. Consider this collection is C, and N naught belongs to I. Then obviously this, now consider one fixed G N naught from this collection C and N naught belongs to I. Then obviously G N naught be the member of tau, and since this is member of tau, that means obviously complement of G N naught is finite set. That means X minus G N naught is a finite, means X minus G N naught contains in finite set. So this is contain such type of element x1, x2, so on xn. And in this element obviously be the member of X, capital X. Consider one general element xi. Obviously this is member of capital X. That means since X equal to union of G alpha, where alpha belongs to I, that means this xi belongs to this union. Since xi belongs to this union, that means xi belongs to any G alpha I. Consider xi belongs to G alpha I. And here this I varies from 1 to n. That means x minus G alpha N naught contain G alpha 1 union G alpha 2 union G alpha n. X minus G alpha naught contain this set. Now, if we add this point in this subset, then we can tell X contain G alpha 1, G alpha 2 union G alpha n union G alpha naught. And that means from this expression we can tell, and since X is subset equal to G alpha 1, G alpha 2, G alpha n union G n naught, therefore we can write X is equal to G alpha 1 union G alpha 2 union G alpha n union G n naught. That means X is covered by finite number of open cover. So I have got one subcover which cover whole set X. So obviously X is compact, and this is compact in cofinite topological space. I hope my all viewers have understood this is why topological space is very important. All compactness depends on which topological space is indicated. In cofinite topological space, every set is compact. I hope my all viewers have understood. I will stop here. In my next video, I will discuss what is the limit point compact. But this part is very important for higher study. So, at first I will hardly recommend you, please see today's video with pay attention, because in topological space, compactness depends on different topological space. See you soon, stay safe and stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much.